Hi everyone, how you guys doing? Hello Mahi, hi AP, how are you people? So first of all, let me welcome you guys to the Unacademy JEE English. This, as you know, is a brand new channel by Unacademy, which is India's largest online learning platform for IIT. And on this particular channel of Unacademy, every concept of physics, chemistry, and maths are being taught to you completely in English, so that students who are not very comfortable with Hindi are also have some place to learn without feeling awkward due to extensive usage of Hindi in most of the content available on YouTube. Now, this is a series that I host for class 12 students, and we are aiming to quickly help them revise their class 11 topics before their JEE exam in February. So, this is the last topic of class 11 that we are covering right now. This is waves, and this is quick review part 5 of waves. Now, before we get started with today's lecture, let me introduce myself for those of you who might not know me yet. So my name is Rohit Dixit and I studied mechanical engineering from IIT Delhi. And for almost past 8 years now, I've been teaching physics for the IIT JEE exams, both mains and exams, advanced. Okay, so for almost 7 years, I've taught in offline setups, and offline I had been associated with some of the topmost institutes that you know of in the field of JEE preparation. Next, I myself, as a student, was All India rank 447 and All India rank 192 in the two stages of the IIT exams that I took. So right now, like you have IIT in two stages, mains and advanced. Back when I took it, there also it used to happen in two stages. Again, those two stages had different names though. So in the first stage, I had secured an All India rank of 192. In the second stage, I had secured an All India rank of 447. And I also had qualified NTSC Stage 2 as a student, and I was in the top 1% in the NACP exam as well. So in my offline years of teaching, I've coached many students to top ranks in IIT JEE, both mains, advanced, and to top ranks and selections in various other examinations as Olympiads and KVPY, etc. Today, which reminds me, was the KVPY. I don't know how you guys did it. Yeah, I hope all you guys who are taking that exam did well. All right, so uh, let's just get started about how you guys students can make sure that you are getting the best possible education even in this time where most of the students have hardly any access to any uh, teachers. Forget about the best teachers. So you guys can go for the Unacademy subscriptions. This subscription will give you benefits like live classes where you get to interact with your educators on a regular basis. Then you also have live polls and leaderboards in these classrooms. And of course, you have test series and analysis sessions on a regular basis, which will keep you on your toes and aware of your standing in the competition at all times. Finally, you have live doubt clearing sessions also. So on all Unacademy Plus courses, every fourth session is supposed to be a live doubt clearing session. Okay, so that's a wonderful feature which will keep you completely free of all your doubts. So after every three teaching sessions, you have one entire session dedicated towards solving the doubts of students, where students are free to ask their doubts, be it about their problem solving or be it about any concept that they did not follow. So with this feature, I think no students will feel that their doubts are getting piled up or left unresolved. All right. So along with these benefits, of course, the greatest benefit that you're getting is you're getting the chance to study from the topmost educators from all across the country from the comfort and safety of your home. So that I think is a wonderful feature. Okay, that allows you again to be safe and study from the best and get the best quality education even in this time. Okay, so all you need to do for getting all these benefits is to get the Unacademy subscription. So how do you go about those? So the first step involves for you to install the Unacademy app. Now you will realize the moment you do that, you will unlock for yourself a lot of features like free courses. Okay, so there are free courses going on the Unacademy Plus app. So you can directly enroll in those just after having installed the Unacademy app. Plus, you can attend special classes. Okay, again, all you need to do to attend these is just to install the Unacademy app, and that's it. That's it. You can start attending these special classes. And finally, you have quizzes. So all these free features you can simply avail just after installing the Unacademy app. No subscription is needed for students to avail these free features. All you need to do is install this app, and you will be asked a welcome code. So you can use this code RD Live, which is my code, and you will be able to unlock all these features. Okay. Now this when you avail these features, so that will give you some idea of how your preparation is going to be with your plus subscriptions. And if you feel that this is the way you want to go ahead, and if you want to take your preparation to the next level now, then you can go for the plus subscription, and these are the steps that you need to follow for that. So first thing you need to do is go to the plus section of your app, select your goal as IIT JEE, and click on the get subscription button. All right. Now, the moment you do that, you will be redirected towards the payment page, where you will find a box that will say, do you have a code? So that is where you can enter this code, RD Live. So when you enter this code, you will get a 10% off on all your subscription fees. Okay, you can now choose from Plus or Iconic. In both, you will get a 10% off. The fees of these two subscriptions are as mentioned here. Now, you will also realize, so you can pick a subscription that suits your study needs. And when you click on proceed to pay, you will also get a lot of no cost EMI options to choose from, so that you can break this payment into smaller amounts and pay this fees in multiple go, to reduce the burden. Okay. Finally, those students who don't know what the Iconic subscription is, let me just quickly tell you about that. The Iconic subscription is a relatively new offering by Unacademy, and this will take your IIT JEE preparation to the next level by allotting you personal coaches. Okay, so from our team of experts, you will be allotted personal coaches. These personal coaches will personally mentor you and guide you throughout your IIT JEE journey, and you will be attending a lot of IIT JEE workshops, receiving expert guidelines from time to time, getting a study planner, and getting regular test analysis sessions. So these are the extra benefits that you get apart from your regular plus subscription benefits. So with all these extra benefits, you will power through your IIT JEE journey. Now, for students who have just entered class 11th and are worried about how to take care of their studies for the next 2 years, you don't need to worry one bit. So Unacademy now offers you combo subscriptions. These combo subscriptions offer you complete package for your preparation of class 11 CBSE studies, class 12 CBSE studies, hence your board preparations, your IIT JEE mains preparation, your IIT JEE advanced preparation. So all your study needs for the next 2 years can be taken care of by any of these subscriptions that you can choose from. So there are 4 subscriptions available. The first combo subscription provides you the Iconic subscription for IIT JEE and the Plus subscription for CBSE 11th and 12th. This combo starts at around 4,600 a month. Then the second combo offers you the Iconic subscription for all three, and this combo starts at around 5,500 a month. Next, you have another combo which offers you the Plus subscription for all three, and this combo, of course, starts at roughly 3,000 a month. Finally, you have a combo which offers you the Plus subscription for IIT JEE and Iconic for class 11th and 12th, and this combo starts at 3,900 a month. Okay, so again, depending on where you think you need to focus more and depending on your personal study needs, you can choose a subscription that suits your needs and then leave all the worries of the studies for the next 2 years behind. Next, students who are following us on the JEE English channel of YouTube, do not forget to connect with us on the Telegram app using this link. So this link will make sure that you are receiving all the timely notifications of every lecture and session happening on this particular channel of YouTube, so that you're not missing out on any of the amazing content being provided to you completely free of cost. Next, so finally, let's get started with today's quick review, part 5. Okay, today we'll be talking about waves. So hello Amod Kumar, how are you? So last time we discussed about beat phenomena, we discussed about standing waves. Today we will shift our focus on sound waves. Okay. So when we talk about sound waves, we usually can divide the sound waves into many categories. So first is infrasonic waves. So you have audible waves, and then you have ultrasonic waves. So that's the broad category in which you can divide these sound waves. Okay. Now, infrasonic waves again are longitudinal waves having frequency below 20 hertz. Okay. Now, these cannot be heard by human beings, and they are produced by earthquakes. Okay. Now, infrasonic waves are heard by snakes, however. All right. Then you have audible range. Of course, everybody must be aware. These lie in the frequency range of 20 hertz to 20,000 hertz, and these are called audible range. This is the range of frequencies that the human ears can detect. Okay, again, you will realize one thing very important. As you age, you tend to not hear the higher frequencies. So you have certain apps based on that. They will play certain frequencies, and if you can hear them or not, you have to respond. Based on that, they can predict your age. All right. Then you have, of course, ultrasonic waves, and these are longitudinal waves having frequencies above 20,000 hertz and are what's called ultrasonic waves. They are produced and heard by bats, and they have large energy content. These waves are also used in applications like sonar. Okay, so sonar is sound and navigation and ranging. Okay, we will briefly talk about that also a bit. So this is the broad classification of sound waves. Now, please note that sound waves in air, because sound waves mostly when we are talking about sound waves, they are traveling in air, so they are mostly going to be longitudinal waves, okay, and not transverse. Okay, you know that in air, all waves there cannot be any transverse waves. Waves only travel as longitudinal waves. Okay. Next, again, if I talk about sound wave, a sound wave is a mechanical wave, of course, so it requires a medium and it is a longitudinal wave and can be described either in terms of longitudinal displacement suffered by the particles of the medium, which is called the displacement wave equation, or in terms of the excess pressure generated due to compression and rarefactions, which is called the pressure wave equation. So, in all longitudinal waves, you have regions of compressions and rarefactions, right? So, you could have, when you're describing the wave equation, so in wave equation, we usually write this equation, right? Y equals A sine kx minus omega t. So here the y is representing the actual displacement of the medium particles. Now, in case of sound waves traveling through air, you realize practically it is very difficult for you to measure the actual displacement of air molecules, right? So we choose an alternate method of representing sound waves, which is by describing the pressure variations when a sound wave travels. So whenever a sound wave is traveling, you realize, so whenever a sound wave is traveling, it is causing pressure variations in the medium. So pressure variations are practically easier to measure. And that is why practically we want to describe the sound waves as pressure waves. Okay, and we write a pressure wave equation. Okay, again, we will try to relate that. So this is how you can write the pressure wave equation. Pressure wave equation is delta P, which is the change in pressure or variation of pressure, which is equal to delta Pm, which is the maximum variation in pressure, into sine of kx minus omega t. Okay, so here is an equation that has been shown to you is the graph. So you have been shown that imagine that this is the variation in pressure. This is the actual motion of molecules, and molecules can be represented as roughly spring block systems. And then you have the variation of pressure. So you realize. So again, the pressure variation from the mean can be denoted like this. This is a pressure wave. Okay. So imagine this is a displacement wave, and with the help of this, you can write the pressure wave. So these regions would have had a high pressure area, and this would have been normal pressure, and this would have been low pressure region. Okay, so you would have had alternate high pressure and low pressure regions. Okay, so that is the entire idea of this wave. Now, how do you get this equation? Okay, so we can talk about that also. Okay, so I don't know if you guys would want to see the derivation. Okay, let me try and show you the derivation also. So what we do is for the derivation, I consider a small section of the medium. We consider a small section of the medium, and let's say from some y, mean some y and y plus some delta y. Okay. So if I consider this medium at any time, if the displacement equation is y equals a sine kx minus omega t. Now, what you will realize is that the current volume, if the area of cross section is S, if the area of cross section is S, then the current volume of this section that we have highlighted, current volume of this section, what will that be? V would be S times delta Y. Okay. Now, at any time t, imagine that these are initially at mean positions. I've imagined that initially both the particles were at mean positions. Now, at any time t, this particle would get shifted from its mean by some amount. Okay, let's say this gets shifted by dy1 and this gets shifted by dy2. Okay, so what will be the change in the length of the section? So can I say change in the length of the section, delta L would be equal to dy2 minus dy1. Okay. Now you will also realize this is nothing but delta y times del y by del x. Okay. So yeah, should have been x and x plus y. This is a particle at x and x plus delta x. Okay. Because x represents the position, y represents the displacement. Okay. So the initial volume would have been S delta x, and finally the change in length would have been the displacement of the first particle minus the displacement of the second particle minus the displacement of the first particle, and that can be written as this. Okay. So what you realize is from here the change in volume delta v would be equal to S times delta x del y over del x. That is the change in volume of my region. Now I already knew this v, so therefore I already had this one equation, and now I have this second equation. Okay, from these two equations, from equations 1 and 2, what I can say is that delta v by v equals a del y over del x. Okay, once I divide these two, this is the expression that I get. Now, once I get this expression, now you know that delta p over minus times delta v by v is equal to beta, which is the bulk modulus. Okay, I hope you guys remember this. Okay. So from here, what I realize is delta P, which is the change in pressure, is minus beta times delta V by V. So I can rewrite this as minus beta times del Y over del X. Now, if you differentiate this equation with respect to X, you realize del Y over del X is nothing but K cos of Kx minus. Right, so substitute that here. So delta P becomes minus beta ak cos of ax minus omega. This is called the pressure equation. Okay. So if you have your displacement, okay. So sorry about that. That was some small glitch. Right. So I think we are back now. Okay. So as I said, this you realize is the change in pressure. Okay, change in pressure of our segment that we are considering. And this will be the peak change or the maximum change. The maximum change that you can achieve in pressure is beta ak. Okay, so once you knew the displacement equation, now you can also predict the pressure equation. Okay, similarly now you can also predict the density equation. Okay, so density is another thing whose variation you can practically easily measure, and that is why I said that these equations sound wave equations are usually, instead of being represented as the displacement equations, waves are usually represented as either pressure variation equations or density variation equations. So you also remember we just calculated delta V over V equals del Y over del X, correct? You also know P into V, sorry, rho into V is constant. Rho into V equals constant, which is M. So if I differentiate this, I realize is delta rho V plus rho delta V is equal to 0. So from here, what I can say is delta rho is equal to minus times rho delta V over V. Okay, so again, I have a delta rho equals minus rho K, K cos of Kx minus omega t. Okay, so again, if you had the displacement equation, then you can easily now predict the density equation as well as the pressure equation. Okay, both the equations exactly vary in the same phase. You will realize whenever the density is maximum, the pressure will be maximum. That is why you're getting two equations which are completely in phase with each other. And the amplitude of density variation, which is the maximum variation in density, would be given by the term rho Ka, and that for pressure would be given as beta rho K, beta Ka. So that is how I had written those equations earlier. Okay, so this is what you need to remember. Okay, now let's try some questions then. Geo net very slow. No. The problem was with my net. AP. Actually, I got disconnected for a bit. Okay. It's not the problem with your net. My problem was my net got disconnected for a bit. I had a power fluctuation. Anyhow, you guys can try this question. So quickly try this and let's see if you can figure this out. This says corresponding to a displacement equation, y equals a sine kx plus omega t of a longitudinal wave, find its pressure and density wave. The bulk modulus and the density, mean density have been given to you. Yeah. So write the pressure equations. Yeah. So this should be super simple, right? So if you remember the derivations or the final forms also, this should be super simple. So let me write it for you. So you know displacement equation is y equals a, and then I have sine of ax plus omega t. So therefore pressure equation can be written as delta P equals minus beta A K. Okay, there is the minus. I wrote the minus a mistake. Yes, so when you differentiate this, so there will be minus. You're differentiating a sine function, right? Oh, there was a minus in this. Right. That's fine. So again, the pressure equation would be minus beta AK cos of X. Similarly, the density equation would be delta rho equals minus of rho AK cos of Kx. These will be the corresponding pressure equations and density equations. Okay. All right, my height. Okay. Okay. So very simple. Again, all you need to do is just remember this form. Okay. And the questions from this are pretty easy only. Okay. Next. So here is another question. You have been asked, what is the displacement amplitude for a sound wave having a frequency of 100 hertz and pressure amplitude of 10 pascals? Okay. Okay. Yeah, that's. I think more data should be given to you. Oh, okay, okay, okay. Cool. Okay, so try this. Hmm. Tough one. So you need to know one more thing about this. Okay, so the speed of sound is root of beta by rho. Okay, so this you can use. Okay, so from here what you can see is beta equals c square rho, and you know a is equal to delta p over beta times k. So you have delta p over beta is c square rho times k. K is 2 pi over lambda. Okay, so what you can do is again cy lambda is new. So what you realize is that this is delta p over 2 pi c rho. Okay, that is it. So you just have to rearrange the coefficients a bit. Now the frequency is known. It is going to be assumed that you know the density and the speed of sound. Okay, then you all you need to do is substitute the values. Okay, and that is how you would have solved this. Yeah. So one more thing, let's before moving on to Doppler's effect, let's also talk about the speed of sound here. Okay, so that slide is missing here. So speed of sound here. So in general, in any gas, speed of a wave, speed of a wave. Again, I'm not going to show you the derivation. I'm just telling you the result. C is root of beta over rho. Now, assuming the propagation to be isothermal, okay, which I think Newton did. Yeah, assuming propagation to be isothermal. Would you realize is that PV would be equal to constant isothermal. So what you realize is that delta P V plus P delta V equals 0. So what you realize is that P equals minus delta P over delta V over V is equal to beta. So P equals beta. So in that case, C becomes equal to root of over a rho, where P is the pressure. Okay. Similarly, assuming now also assuming adiabatic propagation. Again, so Newton assumed the propagation to be isothermal, but that was not the case. It was changed later. It was corrected. Okay, and it was told that the propagation is actually adiabatic. So when if you assume the adiabatic propagation, what you realize is that again PV to the power gamma is constant. Then you differentiate that equation. What you realize is that beta will be gamma times p. So c becomes equal to root of gamma p by rho. So these are two expressions that you really need to remember. Okay, you will be using that. Okay, these two equations we use a lot. Okay, that's the speed of sound waves in any air or any gaseous medium for that matter. Okay. Now for air, you usually take air to be diatomic because major constituents of air are in fact nitrogen and oxygen, which are diatomic gases. So gamma is taken as 5 by 3. Sorry, 7 by 5. Okay. So do remember these, right? Now you can also replace these in other terms sometimes. What you can rewrite this as again, you also know, since P was by mRT, where m is the mass and capital M is the molecular weight. So you also know P over rho and written as RT over M. Okay. So sometimes you can also rewrite this as root of RT over M, which is also a very important form. Okay, and this again can be written as root of gamma RT over M. Okay. So sometimes we use this form also, very useful form. You must remember this. All right. So that is all that I needed to talk to you about sound waves. I think if you followed everything, then you should be fine with sound waves now. Okay, so just the different thing is that sometimes you need to express the sound wave equations in terms of pressure variations or density variations, and now you know how and why. Okay. Now let's move on to Doppler's effect. Again, a very important topic. I think out of the entire chapter of waves, this is the most important topic. If you see the previous questions of JEE Advanced, at least they have the habit of asking at least around one question on an average. They have asked every year. Okay, almost one question is there every year from Doppler's effect. Okay, so this is something that you should pay attention to. Okay, at least for advanced, advanced people really love this topic. Even in mains, they do ask this frequently. Okay, all right. So what is Doppler's effect? The apparent change in frequency of sound when the source of sound and the observer and the medium are in relative motion is called the Doppler's effect. Okay. So Doppler's effect is what? So when a source and an observer and the medium, everybody is stationary, then what happens is whatever frequency this guy is emitting, that is the frequency received by the observer. But the moment they start relative motion, then what you realize is that the frequency heard by the observer or detected by the observer is different from that emitted by the source, and that difference is called the Doppler's effect. Doppler's effect takes place in both sound and light, by the way. Please do not forget it takes both in sound and light. Okay, in fact, it can take in all waves, but mostly we talk about sound and light only. Okay. Now, the sound in sound, it depends on whether the source and observer are both in motion or either one of them is in motion or not. Okay, and there has to be a relative motion along the line joining them. Okay, however, in case of light, the change in frequency depends on whether the distance between the observer and the source is increasing or decreasing. Okay, so again, in our JEE syllabus, the light's Doppler effect is not there. We only have to focus on Doppler effect of sound. So once I think in if I'm not wrong, in 2016 or 17, they had asked Doppler's effect of light as well. But again, that is not in syllabus, should not have been asked. Okay, so we will focus only on Doppler's effect of sound. So first, we want to see the effect of the motion of an observer when source is stationary. So imagine. So here is a source, and imagine this is emitting a frequency f naught. Okay, imagine the source is emitting a frequency f naught, which is traveling in this medium, which with a speed c. So c is the wave speed. Now, what you realize is that every two waves, So whenever one sound wave is emitted, after some time another wave is emitted. So every two waves have a distance which is lambda. Okay. So these are the wave fronts which are oscillating in the same phase. So lambda is defined as the distance between two wave fronts oscillating in the same phase. Okay, so I can calculate you lambda. Okay, so for you I can tell you that if f naught is the frequency, if f naught is the frequency, so how many? What is the time period? Time period is 1 over f naught. So that means when one wave is emitted, the second wave is emitted after a time of a time period, right? T. So in the meantime, the second wave, so imagine this got emitted, and now after time t, the second will get emitted. So till this time, this guy was moving with a speed c. Can I say lambda would be c over f naught? Okay, so this is the distance between the two waves traveling. Now, the observer is, let's say, traveling itself with some velocity VO. So case one, observer traveling towards the source. So what you realize is that the frequency heard by the observer would be the amount or the number of waves it intercepts in 1 second. So in 1 second, the velocity of the wave becomes c plus VO. Okay, c plus VO. So the number of waves, the distance it actually of waves it intercepts in 1 second. So in 1 second, basically, this guy would have moved by a distance v naught. The air waves would have come by a distance c. So with respect to observer, the waves would have traveled a distance of c plus v naught. In a distance of c plus v naught, how many waves would have been there? So f would have been c plus vo over a lambda. Okay. So that is the entire logic. You find the lambda, which is the distance between two waves. Then you find how many waves can this observer intercept, or I can say in the reference frame of the observer, the velocity of the wave is c plus v observer. So I know the wave velocity, I know the lambda frequency is wave velocity over lambda. So what you realize is that this becomes equal to f naught times c plus v observer over c. So the frequency that the observer will hear will be higher than the frequency emitted by the source. And that is a Doppler's effect. अरे क्या हो गया भाई कहाँ जा रहा हूँ मैं? Okay, now we will consider the case 2 also. Case 2, if the observer is traveling away from the source. कहीं नहीं जा रहा भाई शिवम क्या हो गया? Case 2, observer away from source. Okay, okay. So we will talk about that later maybe, not right away, not right away. Okay. उसके बारे में बाद में बात करते हैं जरा, है ना? Let's see. All right. So again, if the sound source is here, an observer is moving away with a speed VO, then you realize, and don't worry, I'm always there with you. को छोड़ के थोड़ी जा रहा हूँ, स्टूडेंट्स को छोड़ के नहीं जा रहा हूँ, उसकी टेंशन मत लो. So now what I can say is, in 1 second, the waves, the or the speed of of waves with respect to the observer would be C minus V observer, and lambda I already calculated is C over F naught. So therefore, frequency would be C minus V observer over lambda, which is F naught C minus VO over C. So the frequency heard by the observer this time reduces. Okay. So if the observer starts to move away from the away from the stationary source, he hears a smaller frequency, which is smaller than the frequency emitted by the source. And if he starts moving towards the source, then the frequency heard by him is greater than the frequency heard emitted by the source. Okay. Next, we will take up another case where the observer is at rest and the source is moving. Now, what is happening here? Again, try and visualize this. Okay, so maybe I will and draw another diagram. In this case, what happens? Let me show you with the help of a diagram. Okay, so imagine a source was here. The source was initially here, and it emits a wave. Okay, so the wave starts to travel with a speed c about this center, correct? So in some time t, the wave would have traveled a distance of, let's say, in 4 seconds, would have traveled this distance. A sphere of sphere of radius 4 times c, correct? So something like this. It would have spread in this kind of a circle. Okay, just try and visualize. So I'm super bad at drawing. So try and bear with my drawing and try and visualize this. I will try to do the best that I can. Okay, so imagine this is what the wave is spreading like. Now, after 1 second, let's imagine if the source was moving with a velocity of v source, and after 1 second it moves here. Okay. Now, after 1 second, what happens is, let's say, when it emits another wave now, it travels again all around with a speed c, but it travels for less second than the previous wave, and it travels with its center here. So what happens is that when this is traveling, this becomes the center, and this is the radius. So this is where you see the wave after, let's say, 4 seconds. Yeah. The center has shifted and the radius is small. How to solve any mechanics problem in JEE Mains, which is the best problems book for JEE Mains? I think all you need is practice. I think if you've solved it at CV, then all you need is just basic practice question papers, PYQs, and I think there are question banks by Arihant. I think they are pretty decent. You can solve those. Okay, you just need practice. For mains, you don't need too much. Okay, you don't need to do too much. Again, in after 1 more second, the source would have shifted here, and the wave emitted when the source was here would have traveled for again 1 more second less. So after 3 seconds again from here, you would have seen that this wave would have traveled probably in this radius. So this is the wave motion that you would have seen. That is how the waves are progressing. So the waves are progressing in spheres of reducing the radius, and their centers are getting shifted. So as a result, what you see is that they are crowding in this area. These waves are crowding in the area, in the direction in which the source is moving. Okay, so if the source is moving in this direction, then they crowd in the direction where the source is moving. They are getting away from each other in the opposite direction. And in the perpendicular direction, they are almost unchanged. Okay. So that is what is happening when a source is moving. The lambda in this direction decreases, lambda in this direction increases, lambda in the perpendicular direction remains unchanged. Okay, so that is what you can say about this. So in this direction, in this particular direction, lambda is unchanged. Okay, so that is how the frequency shift is being observed. Okay, so that you can see from here also. The waves getting radiated are getting concentrated or closer to each other in the direction in which the source is moving. Okay, and they are getting farther away from each other in the direction opposite to the motion of the source. Again, in perpendicular direction, there is almost no change. Okay, so if the source moves. So what is the distance between two consecutive waves? If I had to find out the lambda, which is the distance between two consecutive waves, so how do I do that? So let's say a source emits one wave. So that wave starts to travel. Okay, that wave starts to travel, and let's say it reaches here. Okay, and the next wave would be emitted after a time t, which is the time period of the waves of the source. So in time t, this wave would have traveled a distance of t times capital T. Okay, at time t, the source would have again traveled forward with a speed of Vs. So this distance would be Vs times t. And this is where it will emit the second wave, right? And the second wave will now get emitted from here. And now, once these two are emitted, then you realize both of them will move with c only. So this distance between them will never change now. Okay. So this is the apparent lambda. Okay. The distance between the two consecutive waves is changing, and that is what we are calling apparent lambda. So in such a case where the observer is at rest, what we realize is for such a case, what is lambda? Lambda is c minus v of source times t. Great. So that is my lambda. Now, with respect to observer, also for the observer, the wave velocity, wave speed is still c. Okay, because the observer is stationary. Therefore, frequency heard by the observer would be c over lambda. So this let this be lambda dash. That would be c over t times t minus of source. Okay, and I also know that if f naught was the frequency, f naught would be equal to 1 over t. Okay, where f naught is the frequency emitted by the source. So obviously, this becomes f naught times c over c minus v, okay, where vs is the speed of the source. Now, for the opposite direction, so if the source was moving away from the observer, you will realize that lambda dash would be equal to c plus vst. Okay, they are already moving away. The waves are moving away, and the source is also moving away from the waves. So that will increase the average distance between the two waves. So therefore, frequency would have become f equals c over c plus v. So the apparent frequency would have decreased when the source is moving away from you, and it would have increased when the source is moving towards you. Okay. I hope that is clear. Now, of course, when both the source and the observer are moving, then both the lambda and the c change. So in this case, yes, both lambda and c change. And now I can write f equals f naught. I can simply combine the two equations. Okay, find the lambda dash, find the c dash, and find the result. So c again, you had plus e naught. This is the conventional way of writing. Okay, This is the conventional way of writing it. So this is finally that the final form of Doppler's effect equation that you have. Okay. When both are moving, you will realize both the frequency and the speed of the wave will change, and hence the change in frequency can be obtained by this equation. Okay, where VO is the observer speed and Vs is the source speed. Again, the observer speed is taken positive when it is moving towards the source, and negative when it is moving away from the source. Same for a source. You will put the Vs as positive when it is moving towards the observer, and negative when it is moving away from the observer. Okay. Okay. Now with that, let's try one question. Okay. Let's quickly try this question. This question says two tuning forks with natural frequencies of 340 hertz each move relative to a stationary observer. One fork moves away from the observer while the other moves towards the observer with the same speed. Okay, the observer hears beats of frequency 3 hertz. Find the speeds of the fork and take the speed of sound as 340. Okay, so this is an interesting question, and this is how most of the questions on beats are asked. In fact, so they usually, especially in advanced, they hardly ask any question directly from beats. They like to couple uh, the phenomena of beat or beat frequencies with Doppler's effect. Usually, if you notice all the previous year questions, that is how they have asked most of the questions for the beats. Okay, they've usually coupled it with Doppler's effect. All right, so try this. Let's see what you can do about this. Again. Please note that the speeds are not the relative velocities. Here you do not put the relative velocities because you know observer speed is going above and the source speed is going below. So it's not the relative velocity. Their individual velocities have individual effects. Okay, so do not ever put the relative velocity. Okay, that will give you the wrong answer. And one more thing, I think. Yes, in what reference frame should I take these velocities? These velocities are in the reference frame in which you have taken the C. Okay. So in whatever reference frame you have taken, considered the C, in that reference frame, you have to take these velocities. Okay. Please note. All right. So try this. Okay, this should be easy only. Shouldn't be too much of a problem. So quickly try this. जल्दी कर लो. Okay, so any idea? No. ये समझ में आ रहा है कैसे करेंगे? Okay. Okay, so let me only solve this. So you guys are too lazy, I think. This is an easy one. How can you guys? So imagine here is an observer. Here is your source one. Here is your source two, and you've been told that one fork moves away from the observer while other moves towards the observer with the same speed. Okay, so let's say that this guy is moving towards with V, and this guy is moving away from. Okay, so the frequency of the first source that this guy hears, observer, our observer is here. The F1 heard by it would be for the first source. The source is moving away. The source is moving away, so the frequency heard would be reduced. Okay, so that would be C F naught over C plus V, correct? Now, for the second source, frequency would be increased and he would hear something like this. Now, since the observer hears three beats, so that just implies F2 minus F1 equals 3. Okay, so what I realize is that F naught C times, sorry, not C times 1 over C minus V, 1 over C plus V equals. Okay, so using this equation, I will simply solve for the V. Okay, F naught, here you will have C minus over minus. Now, I will take an approximation. Usually, your C would be much greater than the speed of the source. Okay, assuming is much smaller than C. C square minus V square can be roughly approximated to C square. So what I realize is here this and this gets cancelled. 2V equals, and this would be C over F, or V would be equal to 3C over 2F. So let's just substitute the values. 3 by 2, 2, 340 over frequency is also 3 hertz, 340 hertz only. That roughly gives me the speed as 1.5 meter per second. So fine, this approximation is absolutely correct then. Okay, I was justified in taking that approximation. The speed is roughly 200 times more. C is roughly greater than 200 times V. Okay, so it's a justified equation. Okay, approximation. So usually you usually keep this approximation if there is a factor of 100 only. Any factor above 100, you can use the approximation. Okay, so the speed of both the tuning forks is 1.5 meter per second, and that is your answer. Okay, I hope everybody followed this. Very simple, very simple. So the questions of Doppler's effect are usually very simple. So even though advanced people try to make the situations tricky, but if you have your fundamentals right, if you know your concepts well, then trust me, they are very easy to solve. All right. Well, let's try another one then. So here, this one says when both and observer, when both source and observer approach each other with speed equal to half the speed of sound, then determine the percentage change in the frequency of sound as detected by the listener. They both are approaching each other with a speed of half the speed of sound. What will be the change in frequency detected by the listener? Okay. So quickly try this. Let's see. Okay, I hope you remember the equation when both are moving. Just apply the equation of when both source and observer are moving, and you should be fine. Okay, so I'll wait for maybe 2 minutes for you guys. Okay. So I hope you guys are trying. By the way, this is a simple one. Come on, जल्दी जल्दी बताओ तो बस. Okay, so nobody. Okay, so yes, Pandey is trying. Good to see somebody trying. Okay, AP says 200%. Okay, okay, great. Let's see if somebody else also has an answer. Okay, so yes, Pandey also says 200%. All right, let's see. Let's see. So both the observer and the source approach each other with a speed equal to half the speed of sound. Okay, so I already know the equation of Doppler's effect, that F equals F naught C plus V observer plus minus over V minus plus V source, correct? And these speeds are taken positive when the two are approaching each other, and negative when the two are going away from each other, correct? So I know VO equals VS equals C by 2. That is given. Okay. So therefore, what is my F? F becomes F naught to C plus C by 2 over C minus C by 2. Since both are approaching, both the values would be taken as positive, both would cause an increase in frequency. So what I realize is that F naught is 3 by 2C over C by 2. So this. So what do you realize is F equals 3 times F naught. So therefore, percentage change in frequency. So you guys are absolutely right. The frequency itself becomes 300%, and percentage change is 200%. There's a 200% change in the frequency. Yes, absolutely correct. All right. Percentage change was asked. Percentage change is 200%. Okay. All right. Now there are variations of Doppler's effect, which include questions like reflection of sound. So whenever there is a reflection of sound, so let's imagine you have a source. Okay. So imagine you have a source and you have an observer somewhere here in the middle, and then you have a boundary somewhere. So sometimes these are the kind of questions that are asked of you. So you are told that this source is emitting some waves. Okay. So the source is emitting waves, and these waves are one reaching the observer directly, and second reaching the observer after reflection from a wall. Okay. So whenever you have a wall, so first you need to figure out what is the frequency that the wall is receiving. Okay. So any wall, first you have to realize the frequency it is receiving. The frequency again would be calculated as you will take this as an observer. you will take the wall as the observer. Okay, so if the wall is moving also, then you will treat it as a moving observer. And if the source is moving, then of course you treat the source to be moving. So imagine the wall to be an observer and try to see the frequency it receives. Okay, now the frequency it receives is going to be the frequency it reflects. Okay, because if there are three waves which are hitting the wall per second, so the three waves are getting reflected back also per second. Okay, so for such cases, we first the wall. Again, the wall may be moving. The reflecting surface may be moving. Okay. Hello, Aftab. How are you? Wall to be an observer, and we find frequency received by it. Okay. So first we'll treat the wall as an observer, and we will try to figure out what is the frequency an observer. If had an observer been there with the wall, what is the frequency that they would have received? Now, when reflecting, when reflection happens, the wall behaves as a source of the frequency received. Okay, so for the second part, now you have figured out what is the frequency it is receiving, and for the second part of analysis, you will treat this as a source which will be emitting a frequency that it was receiving. Okay, so you will have to apply Doppler's equation two times. Therefore, Doppler's equation is applied twice. Remember this. If you wanted to consider the effect of reflection, first treat the wall as an observer, then treat the wall as a source. Again, the wall may be moving. Okay, this is not supposed to be a fixed wall. It could be a wall which is being moved. Okay, so in the first case, it may behave as a moving observer. In the second case, it will behave as a moving source. Okay, so you apply twice the Doppler equation, and finally you figure out what is the frequency that is reaching the observer here after getting reflected from this guy. Okay, so that is the ultimate aim. Okay, so why don't we try here? Let's try this problem. This problem says a bat is flitting about in a cave, navigating via ultrasonic beeps. Okay, assuming that the sound emission frequency by the bat is 40 kilohertz during a one fast swoop directly towards a flat wall surface, the bat is moving with at 0.03 times the speed of sound. What frequency does the bat hear reflected off the wall? Okay. So again, you realize purely by Doppler's effect, the bats can realize if there is something in front of them and if that thing is moving or not. So if you're continuously emitting sound waves, if they're coming back, if they're getting reflected back, then definitely there is an obstruction in front of you. Now, depending on what is the frequency that you are receiving, you can also judge whether that obstruction is stationary or moving. So that's a very interesting thing. I think those of you who would have seen that Batman movie, okay, there Batman is using that thing to image people and image their movements also. Okay, so if you've seen that Dark Knight Rises, I think there they've used this, right. There the Batman turns phones into these sonar sources and tries to map every person in the region and their movements using this. So that is the logic or technology that they would have used. Okay. All right. So you guys try and solve this quickly. And let's see how many of you can figure this one out. Yeah. So again, I hope you remember you have to apply the Doppler's equation twice. First, treat the wall as an observer, stationary observer, then treat the wall as a stationary source. Okay. The first case, your bat becomes the source, the wall becomes the observer. So bat is releasing these waves, and for the second case, the bat becomes the observer, moving observer, and the wall becomes the stationary source. Okay, I hope that is clear. Okay. So I don't know if who all are trying. So you can write trying in the chat at least, so that I know who all I'm waiting for. Hmm. Okay. All right. So if nobody is solving this, then why don't I go ahead and show you how to solve this? Okay. So again, for the first part, you have the bat, then you have the wall, okay, and the bat is moving with the speed of, we were told, point 0 c. Bat is moving here with v of bat equals 0.03 c. Okay. All right. So suddenly I've got two answers. So let's see if those answers are right. So for the first part, this is the wall. That is the bat. Right. Here we have our bat which is flying towards the wall. Okay, it is flying towards the wall, right? Directly towards a flat wall. So what is the frequency received by, let's say F1 is the frequency received by the wall. So I can say, okay, no worries, no worries. If F1 equals frequency received by the wall, then what I can say about F1 is F1 would be equal to, so for the first frequency, the bat is the source which is moving towards the wall. So F1 would be F naught times C over C minus V. Okay. So that would be F naught times in 1 over 0.97. Right. Similarly, for the second case, after reflection, after reflection, the wall behaves as a source of, wall behaves as stationary source of frequency F1. Correct. So for the second case, the bat is the moving observer and wall is the stationary source. Okay. So F2, which is the final frequency that reaches the bat. So you had these waves which were traveling, and after reflection, they are coming back. So let's say when the bat receives this back, here's F2. Okay. F2, of course, would be equal to F1 times C plus V over C. So that would be F1 into naught times 1.0397. That would be your answer, which I think should be that what you're saying. Yes, so that is 42.47 kilohertz. Absolutely correct. Well done, people. So this is how you deal with frequencies after reflection of walls. Okay. Next, you have one more case. So again, another variation of Doppler's effect. So Doppler's effect usually advanced likes to ask questions on these variations. So the next variation that we will talk about for Doppler's effect is when the observer and the source are moving oblique to the line joining them. What happens there? Now, if you remember, we talked about this. When the source was moving, then perpendicular to the direction of the movement of the source, there was hardly any change in wavelength happening. Okay. So what you realize is that if you have a source here and if you have an observer here, you have your source, you have an observer, and if we join the line, joining them, and if these guys are moving with velocities of let's say Vs vector, Vo vector again for this guy. So what you realize is that again, the entire velocity that we have taken so far was along the line joining them. So what happens if the source and or the observer are moving perpendicular to the direction? So here, imagine when the source was moving along this line. So if you remember this one, here we said this. Source is moving along this line, and if imagine the observer was here, then you realize this distance is almost the same. The lambda almost doesn't change. So the lambda increases in the direction of motion of the observer. It decreases opposite to the direction of motion of source, and in the direction perpendicular, it almost remains unchanged. Similarly, when the observer is moving, similarly, when you talk about the motion of the observer, what you will realize is again, if the observer is moving here, then the relative speed of the wave according to it changes. When it's moving here, again it changes. It intercepts either more number of waves or it intercepts lesser number of waves. But if it is moving in this direction, then the number of waves intercepted by the observer is not changed. Okay. What we realize is that the velocities components perpendicular to the line joining have no effect on the frequencies. Okay. Again, this is true only for sound waves. In light waves, these components do matter. So components of components of speeds perpendicular to the line joining S and O effect on frequency. Okay, so whenever I have to apply the Doppler equation, I will always resolve these two velocities into these components. Okay, so what we do is we will resolve this and this. So one is Vs parallel and one is Vs perpendicular. Similarly, I will resolve this into VO parallel and VO perpendicular. Okay, now I will only consider the velocity along the line joining them. So when I use the Doppler's equation, now in Doppler's equation, Vs parallel and VO parallel would be considered. That is something very, very important that you need to know about this effect. Again, IIT JEE Advanced has asked a lot of questions about this. Okay, so you should be aware of this. So let's try one question from this. Okay. So the question says a whistle of frequency 540 hertz rotates in a circle of radius of 2 meters with a linear speed of 30 meters per second. What are the lowest and the highest frequencies heard by the observer at rest at a long distance away from the center of the circle? Take the speed of the sound as 330 meter per second. Can the apparent frequency ever be equal to the actual one? That has also been asked. Okay, so the frequencies would be changing continuously, and you've been asked what would be the highest and what would be the lowest frequencies heard by the observer. Okay, so try and answer this quickly. That's all right. That's all right. So how about this one? Try and give me the answer for this one now. Okay. I hope you guys are trying this. Yeah. Okay. So again, this is a simple one. I am guessing you guys should be close to solving this. It shouldn't be taking this long. Okay, so AP says minimum frequency is 495, maximum is 594. Okay. Okay. Let's see. Let's see. Yes, the actual frequency can be heard. Okay. Okay. All right. Let's see. Let's see. So what have you been told? A whistle of frequency 540 hertz rotates in a circle of radius 2 meter with a linear speed of 30 meter per second. Okay. So what you have is you have a vessel moving in a circle. So here is a circle of 2 meters. Okay. So you have a source which is moving in a circle, radius 2 meter, and the source is moving with a linear speed of 30 meter per second. Okay. So now you have an observer which is at rest at a long distance away from the center of the circle. So let's say your observer is somewhere here. Your observer is somewhere here. Okay. So what happens now is, so this is the observer. What happens now is that when while moving, there will be a moment where the source would be moving towards the observer, and there would be a moment where the source would be moving away from the observer, and when in the middle you would have had components of velocities away and towards the observer. Okay, so I can say from the given situation, in the given situation, the maximum velocity of the source away from observer equals 30 meter per second, and also the max velocity towards the observer is also 30 meter per second. So the maximum frequency would be heard when the source is moving towards the frequency towards the observer, and the minimum frequency would be heard when the source is moving away from the observer. Okay. So therefore, what will be F minimum? F minimum would be simply 540 into 330 over 330 plus 30. So that will be the answer. So let's see, that is 540 into 30 over 360. This gets cancelled. This is 11, 12, and now this is 45. 45 into 11. Yes, that is 495. Absolutely. So that is the minimum frequency. Absolutely correct, TP. Similarly, for maximum frequency, F max, you will realize would be 540 into 330 over 330 minus 30, correct? So this becomes 540 into 330 over 300. This gets cancelled. And this is 11, this and this. So that's 54 into 11. 54 into 11 would be, yeah, 540 in plus 54. So that is, yes, those are the correct answers. Those are the correct answers. Absolutely right. And yes, the actual frequency is also heard. Actual frequency would be heard actually twice in every circular motion. Once when the velocity becomes like this, then you have no component of the velocity of the source which is going towards or away from the source of from the observer. And a second time when it is moving here. So at these two instants, the when the source is releasing the frequency, it has zero velocity along the line joining the observer and the source. So yes, at these instants, the velocity, the apparent frequency will be equal to the actual frequency. Okay. So yes, all your answers are absolutely correct. Well done, guys. All right. So again, this is the last variation that we need to consider for Doppler's effect. So this variation says, what if your observer and source are accelerating? So what happens if your observer and source are accelerating? Then what? No, what? Okay, so suppose, let's talk about observer accelerating, and your observer was moving with an acceleration of, sorry, source is accelerating. Source was accelerating with an acceleration of a. Now you realize that the lambda apparent in such a case, lambda would be equal to, okay, so let's imagine some u starts with u s and is accelerating with a. So lambda would be c minus us t minus half a t square. Now, usually what happens is that the time period of the frequencies that we are hearing is very, very less. Now, usually, usually t is very, very small, is very small. Now, how can I say that? You realize t was 1 over nu. Now, whenever we're talking about sound waves, so sound waves are the waves that we can hear. So, and so nu has to range between 20 and 20,000. So so t is at least 1 over 20. So what you realize is, therefore, t square is almost tending to 0. T square's maximum value would be 1 over 400. So I can almost always ignore that. So what we usually do is, we ignore this, and what we realize is that Ct minus UST. Okay. So where US is the speed of the observer of the source when it emitted a particular ray. So all you need to do is where to s equals speed of source when it emitted a particular frequency. Okay. Similarly, when we talk about the observer, similarly for observer, VO is taken at the instant the observer receives a particular frequency. So you will be using that same Doppler effect equation. Okay. So we do use F equals F naught, again C plus V observer over C minus V. But except for what values of V are we taking? So we are ignoring the acceleration effects due to acceleration unless the acceleration is very, very strong. So just remember that VO is speed of observer when it receives sound at that instant. Okay, it is the instantaneous speed. Similarly, Vs equals speed of source at the instant it emits a sound. Okay, so that is very, very, very important. Do remember that. So why don't we try one question, and then I think yeah, that is it. That is it. That is where we will be wrapping up today's session. Okay, so let's quickly go over this question then. So source emitting sound of frequency 100 hertz is placed at a distance of 500 meter from an observer. The source starts moving towards the stationary observer, the uniform acceleration of 20 meter per second square. Find the frequency heard by the observer at t equals 5 seconds. Okay. So try this. Quickly try this, and then we will wrap up this session. The last question that I have for you for today. Okay. Okay. So I don't know. This might be a little tough for you guys. So I go ahead and solve this. A source emitting a frequency of 100 hertz is placed at a distance of 500 meter from the observer. So starts moving towards the stationary observer with a uniform acceleration of okay. Frequency heard at t equals 5 seconds. Okay. So here you had your source, you had your observer. Initial distance between them was 500 meters. Now this guy starts accelerating with an acceleration of 20. Okay. So the observer hears the frequency at t equals 5. So let's assume that the frequency be emitted by source at some t. At some time t, it had emitted that frequency. So in time t, it would have moved a distance of so S1. Therefore, S1 would have been equal to 10 t square. Okay. Now, the rest of the distance that the wave must have traveled now, the rest of the distance, let's call that S2. S2 would have been equal to 500 minus 10 t square, and that should be equal to 5 minus t because that is the time that the wave got to travel, right? 5 minus t and into t for t, correct? Okay, so from this quadratic, we can find out the actual value of t, the time where the frequency was emitted. Okay, so that is one way of solving this. Okay, but that is the way of solving. We realizes that square minus 34t plus, so that'll be 150, 170, 170 minus 50, 20 plus 0. So we will solve the t here, and once I have t here, so t would be 34 plus minus root of 34 square minus 8. So obviously we will take the minus root, okay, and v of source now would be taken as 20t. Okay, so once we'll find t from this equation, then we will find a 20t, that will be the speed of the source, and that from that we will determine the frequency heard. Okay. Okay, let me just quickly solve this only. So let's get a quick answer for this. This is 196, okay. 14. So essentially I'm getting t as, actually I'm getting t as before plus minus 14 by 2. Okay. Okay. T is 10. It's weird. It will be greater than 5. Okay, so okay, let me check the data first. I think wrong. Okay, fine. The equation seems fine. Okay, never mind, never mind. The rest the thing. So, all right, all right. From here, I would have found the value of t, and then I would have substituted that and found the value of vs as t times 20, and then use that. F would have been equal to f naught c over c minus, and that would have been the frequency heard. Okay. All right, so that is where I would like to wrap up today's session. We have discussed everything that I wanted to about waves, so that concludes our entire class 11th revision. Okay, I think you guys should be ready now for your class for your mains examinations completely. Okay. Now, before I wrap up today's session, let me just quickly remind you that if in case you are planning to get your plus subscriptions and haven't gotten them, this is how you go about this. Go to the plus section of the app, select your goal as IIT and click on the get subscription button. When you do that, you will be redirected towards the payment page where you will find a box which will say, do you have a code? So that is where you can enter this code, RD Live. So this code will give you 10% off on all your subscriptions, be it plus, be it iconic. The fees of both the subscriptions have been mentioned here. Okay, and you will realize once you click on proceed to pay, then you will be redirected to the you will be given an option of choosing a lot of no cost EMI options also to break this payment into smaller parts so that you don't feel the punch of this burden. Okay. Next, the iconic suppression, if you don't know, is something that will take your IIT JEE preparation to the next level by allotting you personal coaches and giving you these extra benefits. All right. So now students who have just entered in class 11th can go for combo subscriptions, and these combo subscriptions will take care of all their study needs. And so the four combo subscriptions available are: the first combo offers you the iconic for IIT JEE and plus for CBSE 11th and 12th. This combo starts at 45,600 a month. The second combo offers you iconic for all three. This combo starts at 5,500 a month. Third combo offers you plus for all three. This combo starts at 3,000 a month. The final combo starts at 3,900, and this offers you the plus subscription for ITJ and iconic for 11th and 12th. Okay. Now, those of you who like today's session, do not forget to press the like button and do not forget to share it with more and more people so that more and more students can benefit from this free quality content being provided to you by Unacademy. And if you're new to this channel, don't forget to subscribe and don't forget to press the bell icon. Okay? PDF of all the notes, slides used in today's lecture would be available for download very soon. Those students who are following us on the JEE English channel of YouTube, do not forget to connect with us on the Telegram app using this link. So that will make sure that you are getting all the notifications of every session and every lecture happening on this particular channel timely, and you're not missing out on any of the amazing content. All right, so that is where I will take your leave finally. And before I leave you, let me remind you one final time that this is one code. This is very useful. Okay, RD Live. You can use this code to unlock free features on Unacademy app. Unacademy app. Then you can also use this to get 10% off on your Plus and Iconic subscriptions. Also helps you register, enroll various Unacademy events like the Unacademy Combat and the other quiz competitions that are happening. You can enroll in all of them also using this code. Okay. So one code, many uses. Do not forget to keep using this wherever you want. Okay, so with that, I'll wrap up today's session, and that concludes our entire quick revision of your class 11th. I am glad. I think we started this quick review series towards late November, or I think towards early December or late November. I think within 2.5 months we have been able to summarize the entire class 11 syllabus. So I hope now you guys are ready for your JEE Mains examinations. So best of luck from my side. I'll see you soon. Uh, you guys just keep studying hard and practicing hard and keep taking good care of yourselves. Bye bye.